about multimodal contextualized representation or multimodal aligned representations. So we'll revise a bit because I ended a little bit quickly about BERT and the different ways of learning self-supervised those representations. And then we'll go through 3 or 4 different type of multimodal transformers. And finally, we will look at a new generation of multimodal transformer enabled by visual transformers. BERT, if you look in, you remember the self-attention. I know that you're like, okay, that's like 4 days ago. I had a weekend since then. So what's a query? What's the key? What's the value? So the basic concept, and if you remember, the big change is that now my weights, some of the main weights in my model are dynamic. Dynamic in the sense that given different inputs, these attention weights will change. And they will change because they will reflect how relevant each word is to the other words. So this tells me how word 1 is relevant to all the other words. And that will be used to estimate this unique output for that word. And as we discussed, is that we do it 2 things. So one is multiple head, because there may be more than one way the words can be related to each other. But also these weights, these representations that are learned, they're learned as a kind of a shift. So here's my original representation of the word, and the attention is designed, at least in most transformer, it's not a requirement, but most transformer is designed as a residual. Residual in the sense that you are learning here a way of shifting the original information. But it is not a requirement, and we'll see some architectures that do not do the residual, but most of them do in the case. So then, and that's the very intuitive way this was originally presented, and just so that, because you're going to see that often in papers, but this part is the part that I really spent most of the time of last lecture about the attention, the query, the key, and the values. And when I talk about this residual, and there's also normalization, and this is the main core of the transformer. As we discussed, the embedding is enhanced with the input is enhanced with a position embedding, because otherwise we will not know the order of the words. So when you use this, what's really nice is it can be used in a pre-train and fine-tuning. And I know by now, if you've done a little bit of deep learning, pre-training is kind of a broadly accepted concept. In the last 5 years, became a lot more popular. But the idea is that once I train my model, and that's what the BERT is that it will allow me to learn jointly, not only the representation of each word, but I will also add a special character to learn representation of the whole sentence. And the same network will later be used for fine-tuning. And something which is not the most necessary. Originally, you think, why would I train my algorithm always with 2 sentences? And the goal for that, as you will see later, is to be able to learn very nicely that unique representation of the sentence. That's often why you will put both of them during training. And bidirectional, in fact, it's bidirectional. It's more than bidirectional, in fact. It's really every token is connected to every other token. Every word, sorry, sometimes I will use the word token instead of word or input. It's just in language, natural language processing. The word is used as token, often as a simplification, because token could be not even a real word. It could be half of a word because we remove the ending or simplify the word. So that's why sometimes they're called token. So to do this, we use a transformer with a special character at the beginning and a special one to separate. And so how do we train this automatically? That's the BERT. So when you hear BERT, what it means, it's mostly a transformer that is, but it's a transformer plus distributional hypothesis. But how is it called now? Distributional hypothesis? It's called masking. So really the main novelty of BERT was primarily to bring this idea of masking to the transformer and also to bring that extra token, because originally the transformer was proposed as a machine translation but it didn't have that one token, that one output that will give me a representation of the whole sentence. So the main two things, novelty with BERT, was bringing the masking, as we'll see in a second, and also bringing this. But to bring this, they realized that they will need to train with two sentences. That's what they realized also. So the training objective has two lost terms, primarily. One lost term is by the idea of masking word, because we know that words can be approximated by its context, the meaning of the word. And so we want it to be able to predict the original word. So this is the original word, and we're going to compare. In fact, there will be not directly that, there will be a small layer on top just to do a one-hot encoding to get a one-hot encoding. Or what's usually used is, instead of a one-hot encoding, is maybe my words are already encoded in Word2Vec or something. And so I already got an original one, and I'm only just going to predict the one output there. But usually it would be one hot encoding. So, and the last then is over these, the masked one only the masked one. And then finally, it was the question, how would you force this output to be a summarization of the whole sentence? In fact, how do you force it to be a summation of both sentences? And to do that, they design a simple loss, which is just, is the next sentence really the one that in my corpus was the one after the other? So the positive are easy to pick up based on text, one sentence after another. So it's self-supervised in that sense. And you can get the negative by picking any other sentences in that same document, probably, or you could pick in other document, but usually you try to have hard negatives that are close, but not too close, but not exactly the same. So you don't want the next sentence, but you want anything that's close to it, just to see if really your model is able to. So these are the two, and once you train it, it's nice because then you can use it at test time. Was there a question? So yeah, so the idea, yeah, so this embedding will be the meaning of both, but at test time, what you can do is encode. You train it with two sentences, but there's nothing that requires you to use it with two sentences at test time. And so at test time, you can encode only one sentence with that token. But if you end up putting two of them, then this one is most likely a summary of both, or a comparison between both, but mostly a summary of both, yeah. But it can be used for encoding one sentence, or it can be also used for if you're doing any kind of token level or word level prediction. That can be like part of speech tagging or slot filling, for example. Now, if you have two sentences, and that's the one I tried to explain, and it was the end of the class. I was like, okay, let me come back to that one, so that so you can do fancy things with this. And here, there's one of the interesting things they did is it's question answering. And question answering is you have the question, and then you have very long, like I only put the first few words, but you have a very long paragraph of the whole thing. And you're going to fine-tune your transformer. By fine-tuning transformers, most of the time you don't touch any of the weights in the transformer itself, and you're just going to put a layer on top. So I'm going to put a layer, and question answering for people who know this or don't know this. So there's at least two versions of them. One is called more, there's abstractive and extractive. Yeah, extractive. Thank you. So the more extractive approach says, I'm asking you a question, and I want you to just find in the paragraph where the answer is. Okay? Find the start and the end time of where this paragraph is, the answer is. The abstractive will be regenerate an answer based on all the information. So extractive is a little bit easier. So how do you do this here? How do you do the extractive? This outputs you a representation, a contextualized representation of each word, but it doesn't give you that magic. So what's really interesting is that you will add on top two set of parameters. So a linear layer plus a softmax and tokens here. And this is going to be checking, hey, is this a good start? Is it a good start? And so you compare each of your output with the start token. But to do this, I told you that most of the time you will not fine-tune the parameters. But here you probably will need to fine-tune a little bit the parameter because you want the output of this to be contextualized in such a way that it identifies it as a potential good start of a sentence, not based as much on the other words here, but based primarily because of these questions. So the question is going to be self-contextualized, but you want your transformer to also realize, hey, for that question, where will be a good start of that sentence, of that answer? And it's quite amazing that the transformer, by default, the transformer is about contextualizing only. But with the right kind of loss, it can also do more than contextualizing. It also can compare things. And now it's going to do some contextualization of like really understanding the answer. And it will also understand contextualizing what are the words in it. But in later stage of the transformer, it will do a second thing, which is start comparing. And not just comparing is the next sentence of this, but comparing if this part of the statement is a good answer to the question. And you will, how do you get the end? Is in fact, you will have a replication of it, a separate network for the end token. And you just take the max of it, the max value. So you compare in a sense, is this token part or start of my sentence? Start of my answer. In fact, then after that, many people started playing with the transformers, and they use it for just classification. So that's the way I showed earlier. So you have the start of the input. This is the input. It runs through the transformer, and you have a linear the output. But then you can do entailment, which is two sentences, and then you will use usually the output for the start. So here, just to make it clear, so this start and extract, these would be the start token, and there would be kind of an extract token here. Okay, so I'm just plotting this in a more compact way. But then you can do similarity, so you can encode start text 1 and text 2 and see the two sentences. And the last one is the one that is very similar to the extractive, which is multiple choice, like you context and then answer 1 question, answer 2 question, answer 3. So you can change a lot of these from the same transformer. But this is unimodal transformer. What we're really going to study is multimodal version of it. So how do you take a transformer and make it multimodal? What's the simplest way to do it? Early fusion, kind of. Okay, so the simplest way would be to concatenate all of your inputs. Now, for an image, let's say you have one image, then what you can do is take an image and look at it as a list of objects. And so the first simple approach is, let's say, one transformer for all self-attention. So the visual BERT that came really soon after the BERT was mostly BERT. This is BERT. Okay, so the start, and then you have a sentence. Now they're showing in it the training with the mask objective. And then you have a separator. No, not yet. You have a separator, and then you have all the possible. This is for image captioning. So you have the caption and you have the image. And so you have all of the words, all of the objects, and then you will have somewhat of a spatial embedding. So you have the token or image embedding, token meaning the word, and then you will just have like, hey, what is it a token or an image? And then is a position of it. So it's just a more fancy position embedding to the same to the previous representation. And what is the transformer going to do? So this is only weakly aligned. It's weakly aligned because if you think about it, I don't know. I only know that this sentence is related to this, but I don't know that this, like, am I talking about the hand? Am I talking about his nose or his hat in the caption? That's the job of the transformer. The job of the transformer will be to contextualize or link not only the words together, but also the object. Now, in the first version, the objective was only in language. So in that first version, it was only masking the word that was for training. So the object were not masked. But then came an extension to it, the unitar. There are quite a few extensions, but I'm giving you a few of them. Otherwise, I will overwhelm you with all the acronyms. People are very smart on how to pick acronym for this. So the unitar was exactly, each of them has slightly different it looked different, the model, but it's exactly, the basic of it is exactly the same. Yeah, question? Oh, yeah, most of them will start from already an embedded. So I forgot what they use, but there must be a CNN or something like this before, and the transformer was mostly there to contextualize them. I'm almost certain there was for image, for language, it could have been trained from scratch, one-hot encoding, but it is also really possible they had one. I forgot the details of that yet. Yeah, I forgot the details on that exact paper. Some of them will enhance it with either relative position between objects. So the embedding will not, some of them was just absolute position in the image, but some of them were just relative to each other. There was some different exploration on like where they were from each other, because like a man next to the horse or a man on top of the horse will mean something different. And so you want to have that relative information between objects. So usually the absolute is not important, but the relative is important. I forgot if Visual BERT had it, but definitely later on the relative position between objects was encoded as well. Yeah. And so the unitar, the main thing they changed is the loss. Instead of just having this one loss, they had 3 losses. So the first one is the exact same one. So you mask certain words and you see. And by the way, the community in 2 years started using acronyms. So in many papers, they don't even start putting the full name. They will just say MLM, and they will expect that you know what MLM is. And like many of the papers we're going to read and for the reading assignment next week, you're going to see. So MLM, that one is not as popular now, but mask region, which is mostly the same as it, but you mask an image, trying to find its, and usually, as I was asked, it's not the image itself, but it's the embedding of the image. And so when you try to predict, you're not really trying to regenerate the image, but you're trying to regenerate the CNN embedding of that image or that object, really. And the ITM has been, you're going to see it in many papers later on, is the image text matching. And the idea is, if you have this information, somehow which object matches which word, then you can use that, or you can find a way to approximate it as well. So masking the word, masking the image, and is the sentence matching the image. So this was the main one. I mean, the two main novelty were these two, but the main one was starting to match the two together. And so this is one option, which is kind of the early fusion. You just concatenate all of them, but then you put some different loss to make it match together. But then what seemed to work really well for a while, I will say recently, people have started a new way to do it, but because of vision transformer, but up to like a year ago, there was another way to bring the modalities together. And the idea is, instead of doing it all one, let's do pairwise interaction. What it means is that you will have not just one transformer, but you'll have like 6 transformer. And if you think about it, why would you have that if you just do a simple transformer and just concatenate your inputs, and if you use the same weights for the queries, if you have 3 matrices for weight for the query, the key, and the value, but you use the same one for the whole transformer, that means that the same way you encode query for language is going to be the same kind of weight query that you will have for an image. So image and text will need to have the same. If you do a very simple self-attention transformer and you just early input, then you're putting a lot of pressure on those linear transformation, WQ, like the query, W key, like the way you embed keys is probably going to be quite different for an image and a text. And so, yes, you could start in the transformer to kind of split that, to untie the weights in the sense that you will have a weight that's different for embedding language than the way you embed images. By separating to 6 of them, you're kind of untying those weights. That's kind of what it is. The way you're going to encode text with the purpose of being contextualized with image is going to be different than the way you encode text with the purpose of being contextualized with audio. So WQ, when you do text, 30 minutes. So WQ, when you know that you're about, so these 6 arrows, what it means is I have my language and I want to be contextualizing this language with audio. So is there something in the audio that's relevant to the meaning of my word? And is there something in the image that's relevant to my word? That's the 2 transformer for language. And so there will be a separate W query for the first one and a separate W query for this one. So the way language will be contextualized by images is probably very different the way you contextualize language with audio. And that's why separate, what will be called often cross-modal transformers will be learned. So if you have 3, now the problem, it doesn't scale well. If you have 10 modalities, then that kind of approach will be challenging. So you will get two language embedding. So one which is language contextualized with audio, and one which is language contextualized with visual. And then you can either concatenate them, or usually what you will do is a one-layer neural network to just fuse these two together to get one embedding the same size as the original one, but that one has been contextualized by both the audio and the video together. And then you have two more transformers for the audio and two more transformers for the video or image. So and as you know, there will be many attention, so you can have multiple heads to that. When you do each of those transformers, it could be multiple heads. And once you get this embedded one, you could repeat the whole process with another layer of it, where you keep contextualizing each model. And usually this is done in a same thing as before, which is we'll have you're going to learn how to change the original one. So it's a skip connection that you will have as well here. And if you want, at the end, you could take all those three and force them to be in one representation, but there's nothing that forces that. So each of those transformers, what they do, like let's say visual and verbal. So my goal is I have verbal and I want to contextualize it with visual. So visually contextualizing the verbal modality. I have already representation for my words, but I want to add visual information. So let's say I have a word, extraordinary, and I want to see which of these frames, or it could be in an image, which of these objects is related to it. And so I will get my original embedding, get my WQ, and get the image, and get my W queries, and then look at the similarity between the query and the keys. That multiplication gives me my attention weight. And then if I multiply it by my original visual embedding, then I get my correlated visual information. What is it in the image that's relevant to the text? And as we just said, it's a residual connection. So what is it I can add to my previous one? And finally, I get my new visually contextualized representation of language. So this is the key of about 5, and 5 is just the one that are popular. I'm sure there's about 100 BERT that got visual language BERT that came after that. I'm going to bring you a few names, and if you know of another one and I didn't list it, sorry, but I just want to show you a few. But just before that, before I'm about to show you a bunch of BERT versions, I just want to say, when you think about it, when you contextualize, like which one is the query? If you have verbal and visual, and I'm trying to create a new visually contextualized version of language, is language a query or is it a key? It's a query. I'm looking for that. So I want this. So here, language will be my query. And then I have visual, which is be both the key and the value, which means what is it in vision that could be useful to me? And let me see how relevant it is to those exact words. So BERT came out, vision language BERT came out, and really CRM just for transformer. But this is just a cross-modal transformer. Oh yeah, sorry. I didn't show yet, and maybe I should have updated my slides. Let's say for now it's an image with object. I'm going to talk about video BERTs in a little bit. There's different approaches. Some of them are very simple. You take video and you just cluster the video, which is temporally cluster, like hierarchical clustering, for example. Like so you get segments and you will select a representative frame within that segment. So it's very simplified. way. But then you need to update, as you hinted at, the position embedding to include some information temporal. I'm blanking on the details, how they did in the different one, but in general, the same idea as image. The most important thing is less the absolute time, but more the relative time between the segments. So the position embedding will be particularly designed to enhance that idea that two segments are close to each other or not close to each other. Yeah. Yes. But for now, let's suppose it's an image with object just for, yeah. So the main novelty with BERT was a cross-modal transformer. Otherwise, it's just a simple contextualization of the words, embedded probably with the CNN originally, and then we add another transformer just for fun at the end. But this really is the core, the alignment really for that. The hypothesis is that you may want, every time you put a transformer, just think, I want to contextualize word with each other. Now, why was it not sufficient to contextualize here and contextualize it? Maybe there is an extra contextualization that was useful empirically, but the core is really in this component, or for language having a prequel there. And there you see LX-MERT looks very different, but this is almost exactly the same. Cross-modal transformer. It has here in this case, they have many objects. So they will want to maybe have a transformer to look at relationship between objects, and then a transformer to look at relationship between words. But really the core is here, and then the same way they have a contextualization of afterward. But the main multimodal is really that cross-modal interaction. Oh, why would you pick that token to be the one that represents the whole sentence? Or both the sentence and the image, or the content? Because they at least in previous transformers here, they were not putting a token as a sentence token. They didn't have that, although I'm sure you could think of an interesting loss term to be sure that that representation is for the whole image or for all objects. But at that point they didn't. But they had one for the sentence. And since that token ended up in this cross-modal interaction, ended up being contextualized with all words, this token ended up being contextualized with all words, then by the time it's here, this token has been not only already as a representation of the whole sentence, but has been contextualized with all words, all objects. So now by the time it's here, that sentence embedding is contextualized with all objects. So it is, in a sense, a cross-modal output at that point. So I want to also share a third way somewhat of bringing multimodal. And for that, I want to remember, if you remember, like multimodal shift fusion. So you have a modality that you know is a primary modality. Let's say you do sentiment analysis, and language is very important. So maybe you will, instead of saying, okay, all modalities are born equal. No, I will say one modality is going to be kind of my skeleton, my main structure, my main goal, and I'm going to shift from it. So one modality will be the primary, and I'm going to learn a gate to shift this. And so one example for multimodal sentiment, because multimodal sentiment analysis was originally a language task. It was sentiment analysis for language. And I already showed that results where the word expectation could be shifted to be negative or could be shifted to be positive based on the audio and the visual. So now, how do I do a transformer version of that? So here, one way to do this is that you will start with just your primary modality, and you will run it through a transformer, and that gives you your embeddings for the language embedding. And now you will shift that embedding. I'm going to show it in a minute in this how, and then you're going to recontextualize things. after that. And so the shift will be, and this is a design decision, like why would you include this one? It should be only acoustic and visual. The reason sometimes to also put the word is to say how the word is different from the acoustic and visual. Like, is acoustic and visual bringing something different? And if so, let's take advantage of it and shift. And then you have a addition or something similar to addition here to finally get the next embedding. So same transformer, just a different gate there. It's really nice little shift there. And then there was a question earlier about video. How do I handle video? There are quite a few approaches. I'm only going to highlight two or three of them. And they're great benchmarks, like the how-to 100 million. So these are how-to videos, like how to teach a multimodal class. So you will have the video and the series of instruction, and it's a weekly align, because you don't, most of those data sets, you have maybe a caption of what has been said, and then you see how things are done, but you don't always know exactly what is the link between which video and which representation. So if you look at it, the instruction videos, and you look at the captions of those instruction video, you hope that the frame that are shown right now are related to what the person is saying, but it's maybe not a one-to-one mapping. And so when you are in this kind of situation, you have your video and you have all of the current spoken sentence. So this is like the captions, all the possible captions, and then the captions within maybe plus or minus a minute. Okay, and then you have that frame, and you would like to train it together, but it's weakly supervised. So one approach which is called multi-instance learning, and the idea here is it's a really nice objective function, but it says within this, let's see it as a bag of potential. I know that at least one of them is positive. I don't know which one, but I know that at least one of them is positive. And that's what the multi-instance learning loss. I didn't write it down for this slide because I wanted to go through other approaches. But this is a really interesting, simple but interesting approach. It says, I know that one of them is going to be a match to me, but I don't know which one. And then because I don't have labels, then I will add to it a contrastive loss like NC. You remember in N4 NC? So really this approach is mixing together two things, the contrastive loss, okay, with positive and negative pairs. So negative pairs is easy. It's like anything that has been said like 2 or 3 or 4 minutes after, or 2 or 3 or 4 minutes after, these are negative for my contrastive learning. The problem was the positive pairs. I don't have those annotation. Here, I'm going to make kind of, that's where the multi-instance learning, it will say, there is one of them that is a pair for you. And I think this will be one of your reading assignment, one of the 4 reading assignments. If you want more details also for next week. So, but you can also believe in the transformer. You have to believe in transformers, and that's another way to do it, because transformers are designed to identify those alignments. And so one way to do it is video BERT, and video BERT was, as was mentioned earlier, how do you create the visual words is you simply, in this version, is they take the video of the instruction video and use a simple k-mean clustering and just use the centroid of that k-mean clustering as the representative one. So that's a simple one. There was some extension. So for example, the BERT was interesting. So This is BERT. This is the good old-fashioned BERT. There's nothing special there. And here is kind of the same as visual BERT. So you have an image with some kind of spatial position encoding that was asked earlier, like, but these will be especially designed for local relative to each other. And then they will use a stack of frame. So I didn't go in details for that, but there are CNN for video. And so CNNs are by default 2D CNN because it's an image. What do you think the name of the one that goes 2D plus temporal? 3D CNN. So there are 3D CNNs. There's some nice extension on that. There's about true i3D was a good one for a while. It must have been, now I'm sure there is a video transformer. There must be by now, but at least there for a long time these 3D. So you can take a bunch of video frame, run it through a 3D CNN, get an embedding, and then the cool part is that they didn't just do a masking, because that will be the classic, will be to just try to make it so that you get the same frame here, or try to do it so you have the same short video. Here, they were like, okay, within that audio segment, within that video segment, what was the verb that was spoken during that segment? And again, it's not perfect, but so during that segment, the verb was rotate. During that segment, the verb was add, and so that's how they use this kind of weak or noisy supervision as well. So these are the video kind of approach. But now in the last, and that's where I will spend the last part of the lecture today, is there's a new generation of visual transformer, which also brought with it a new generation of multimodal transformer with it. But before I go there, any questions about either the previous one or any of the visual transformer? In the typical visual BERT, because you probably know about VIT and things like this, so you already changed your mind. But if you were taking this class 2 years ago, you will not know about vision transformer. So you will use an RCNN, a region CNN. So you will take an image, you will run the CNN, but as you mentioned, as we talk about, like instead of running the whole thing, we do kind of a image segmentation to know the regions, and then just run the CNN over that. So usually the image one will be an RCNN. I would not be surprised that BERT was using fast RCNN or something like this there. And these will often be video frame simply concatenated over. So they will. You could imagine tracking object over many frames, but I don't think that's how it was done here. Usually it's just a frame and just a CNN, 3D CNN on it. Yeah. Any other questions? Yeah. So the paper has a little bit more detail, but the high level is that these videos are how-to videos. So you're showing something on the video and you're explaining it at the same time. And so because only for that kind of video, this will not work for other videos, or maybe it will work for a lecture video like this one, as long as you look at the slide, but it's not as perfect. Here, what you will hypothesize is if I am if I'm doing something, I'm probably using a verb right now in my sentence that is representative or related to the action I'm currently doing. So that's the hypothesis they use. So they really use, I forgot the exact detail, but they use a very simple alignment saying, hey, that video clip, and I forgot if I don't think they were doing clustering as the previous approach. here you may have the start and end time of a spoken utterance, and then you could use that as your, or at least for every verb phrase, you could go for your utterance and all segment by verb phrases, and for each verb phrases you can have a segment, and now you pick the verb of that verb's phrase, and then that becomes the one there. You could imagine some variants of that, but that would be the one approach to do it. Yeah. So I glanced over that a little bit quickly. Sorry about this, but the idea is that a lot of those how-to videos will be captioned, and so they just went ahead, took the video, took the caption. The caption nicely have a start and at least a start time when they're displayed, and an end time where so that's what their start and end time would be. Yeah. So for some of the let's call them old style video transformer, because they're like a year old. So now there is a new generation of visual transformers. I will focus on image in my slide, but I will not be surprised. I forgot to double check, but I will not be surprised. There's also a new type of video. But right now, the old way of video transformer is to do these either clustering. So in a sense, they are not using the timing, because in this case, I think this video BERT was not done on exactly this kind of data set. So it didn't have perfect start and end time. They may have just a caption for the whole video. So maybe they have a caption for the whole video. So it's more approximate. While if you have these more fine-grained, then you can take when the caption started and when it ended and call it a segment, and then embed it. You could embed it, as I mentioned, by just keeping the centroid of that, like the center frame of that segment, and just run CNN over that, or do a 3D CNN on top of that. Yeah. Okay. So now what we will do is the new generation, and I say new because even I think last year it was there, but it's a year and a half or 2 years max. So I'm going to revisit. I know you're like, oh my God, that's like 4 weeks ago we talked about CNN, but I want to do a little bit of computer vision for like 3 slides, because I'm going to enable a new type. It's not so new, it's so different, but a somewhat new generation of multimodal transformer because of that. So because all the previous one, they were almost all of them using a CNN as an input. So although it's called visual transformer, visual BERT and all this, but the visual part always had a CNN in it. Now we want to get rid of the CNN. No more CNN, all transformer, all you need is attention, okay? So some people know that paper, yeah, good. So the previous convolution is you have an input and you learn static parameters, that will look for a pattern. You're looking for a pattern in the image. Now, the self-attention does something different. Instead of looking for a pattern there, I'm gonna, in a sense, what do transformer do? What do transformer do really well? Is contextualize. So don't think of CNN the way you thought of CNN with template matching. Now think of it as I'm going to take my image and slowly contextualize my pixel with each other, and then pool and contextualize with each other and potentially pool, or at least if I reduce the representation, but I will contextualize. So it's no more the kernel, at least it's not the exact same intuition of like looking for template. Here, it's really about contextualizing. And originally, I will only contextualize my pixel with its neighbor, but at the next layer, that megapixel will be contextualized with other megapixels. and then this with other megapixels, and you go for that. So if you think that way, then you will say, hey, this pixel is going to be my query, and then the neighbors are, including myself, are going to be my my context. And then the question is, am I really similar to my neighbor, or is there any information in the neighbors that is relevant to my meaning? Now, when it's really low, like pixel really level, doesn't make as much sense. But let's say it was objects, okay? And like that will make a little bit more sense. It will be, this is my object, and this is my object on the left, my object on the right, my object in front, in the back. Now it starts to make a lot more sense, the CNN. So in the lower level, the other one was more intuitive, the real CNN, with like the same way that the visual in the brain is working, looking at edges and things like this. Here, it may end up looking for edges also, but it's primarily about contextualizing. But if you look at it at the higher level, it makes sense that the meaning of an object will be related to the meaning of the other object close by. And that's really what it is. So look, think about it more in that sense of objects. Hey, that's my query. The other objects around, this will then, so you have three, the same linear projection as you have in a transformer. You have the same linear projection. And then you get here how well the query matches the key, but more specifically, how well the pixel matches its neighbor, or how well this object matches, or this patch of pixel matches the other patch of pixel. We're not yet at the visual transformer that you know, probably in the transformer, but we're one step from it. But yeah, and then people will call this a memory block, like a context, my neighbors, so the memory block of my context. And then finally, this would be my pixel contextualized by its neighbor. And you can do a few layers of that. And you can also do multi-headed. So you can have more than one way to contextualize. So maybe you're going to start contextualizing with different edges, maybe. But how do we encode position? That goes a little bit with an earlier question. Here, often you will use a relative embedding here. So my pixel is here, and then all the other pixels, their embedding will be relative to the query. So the query and the embedding for the other. So the embedding is not done like previously, like it was the input is done once. The position embedding is done once. Oh, second. Like it's not the same. So in the other, like the position of a word was kind of computed once, and that's it. Now a pixel or a patch will have, every time it's compared with a different query, it will have a different position embedding. Okay, that takes a little bit a while to think that way, but yeah, every time you compare with a different query, although it can be done efficiently, there's a way to done, but the intuition is that you have the query times the key, the typical one, and then we have here they decided to sum them, the position embedding and the key, and they decided to sum them. That's a choice. We talked about it. If you do that, that means that your two spaces need to be the same, or you think about it as this shifting your other space. So either you see it as a shifting, like kind of a residual in a sense, but yeah, so that's a position embedding that's relative to that. So this was one of the first, I think there was an extension to that called image transformer. But then finally, the one that is currently the popular approach is vision transformer, also known as VIT. So the animation goes quickly. I'm just gonna go to this image first. So this is, I have two more vision transformer to show you. This is one, and there's another one, the mask autoencoder. So this one, and it takes a little. So the input is no more CNN. The input is the image, and I will arbitrarily take the image and slice it in patches. Arbitrary. Oh, arbitrary. What does it sound like? It's a hyperparameter. And yes, you have probably hundreds of papers that study the effect of size of patches and number of patches and like rotating them and changing their color and all this. So yeah, but the basic concept is you take a patch, and then as you will see, you will take these patches, the linear projection of these patches, just as we had WQ, WQ, W query. You add an embedding, which is its position. But as you will see, maybe let me run the, so you have the patch, you run them, you have this, and then you have the position embedding. And then from there, you will be able to predict the head, the head of this. But the main thing is that you can shuffle them and also force the transformer to know the ordering of them. So there's different kind of loss. The loss that is shown here is supervised loss. So you know that you have a class, and so you encode the patch in with the position embedding and the patches themselves in the way that you do this. There is also the possibility of randomly swap them and force it to be able to know which position it is, where in the image it is, or where it is to the related to the other as well. So if I give you that patch, I say, and you have all the, I hide this, or I give you this, but I give you all the position of the other, but I don't give you that position. How do I predict that position of that patch? So that will be like, okay, look at all the other patches and see where it will fit in the image. So there's been a few other extension of other kind of losses, but the two primarily, one would be directly a supervised loss, like you clearly want. And I want to emphasize here, you are learning a transformer to be good at discriminating one object, finding an object within it. So it will learn to embed your image, but it will learn to embed your image in such a way that it's really good at that supervised task or that puzzle solving task. But there, bless you. But it's kind of a it's kind of a discriminative task. And the reason I'm emphasizing that is because there is a nice extension or a separate word that is called mask autoencoder, and that's right now what I will say probably one of the nicest auto transformer encoder. And this one will be a generative loss. It tries to regenerate the image. And so I'm going to tell you in a second how it's done. But at the high level, the previous one, CNN included, were all trained to be really good at predicting a class label. That's what they were trained, originally on ImageNet and all this. So in theory, it's possible that if when comparing all the object class, it was not useful to recognize frowning, for example, or any kind of like to know, is it a face or not? You don't need to know the difference between open mouth and closed mouth. Like, what's the difference between this and this? Like, there's no, like, there's things you can completely ignore. Your task is it a person or not? Is it a face or not? So a lot of the subtlety can be lost. Now, those generative models are a lot harder to train, but if successful, they may bring a lot of the subtlety you will want to generate. So to approach it, there was it's mostly the main intuition, and it's counterintuitive at first. It's like you will hide not 5%, not 10%. I feel like a salesman. Not 20% off. It's 70% off. Yeah, 70. And I think I removed the graph from the paper, but 70% of the image will be hidden. So very hard. And now what I will do is I will encode only the ones that are visible, only the ones that are visible. And this encoder is a lot like a visual transformer that I just showed in the previous slide. Okay, so, or just a transformer if you want. This is a transformer that will, its goal will be to encode this. So create an H vector that encode the image. So this will encode every patches. But this is not your loss. But here you take an image and you encode it through many layers of transformer, really. And then you get an H. And then you're going to put those H at the place where they were in the image. So you remember the 30%. This is the 30% that was not, sorry, I don't think the image is exactly 70 and 30, but anyway, take it from me. 30%. And that 30%, you know where this comes from. And so you will put it exactly, this one goes here. So this is the embedding of this one. You put it there. And then you have another transformer, the decoder transformer, that go from H back to the patch. And that will be and then they're just copied in the image. And then you can, reconstruction loss. Not encoder kind of reconstruction loss. So the loss is really an autoencoder kind of loss. You are training it to recreate every details. In fact, a lot of them you don't even see. You're trying to regenerate them. And so mask autoencoder, encode, and at test time, what do you use? Only the encoder. And you can use the encoder with the whole image. You don't need to do the masking at test time. So you give it the whole image and it's going to encode this, and then you can aggregate this information for all the patches together to give you the embedding for it. Yeah. And so is your concern with these or with these? The gray one. Yeah. So the gray one is really interesting. So the decoder, if you remember how the decoders, transformers, let's just call them transformers. Transformer is about sharing or contextualizing each other. So here I have no information at all of what, I only know my position. So there's a position embedding that I didn't plot there, but for each of them, there's a position embedding. So the position embedding say, hey, I'm at this place and it's a relative one. Like I'm at this place in the image. This is my neighbors. And there, where the transformer will say, okay, you don't know where you are, but I know your neighbors. Do the same way I will contextualize in a sentence. I hide a word and I end up being able to learn the meaning of the word, although it was masked. That's what this is going. It's like, hey, I know you would love to you would love to know your meaning. You're being masked. So this is a more typical BERT in a sense. This is a more typical BERT. This one is just a transformer with no masking. But this you should see as more of a typical BERT where the meaning has been masked. But I'm trying to use your neighbors to fill that. Yeah. The amazing thing, to my knowledge, is that not much had to be changed with the transformer architecture to be able to get that. I mean, it's multiple level. It's really interesting to see if you just do one layer or you do like if you go more encoding. But yeah, if you increase the number of layers, it becomes sharper and sharper. And there's both in that paper and there's follow-up papers that show that. But from what I remember, there was not a lot changed to the typical transformer. It was really just the idea of decoding the meaning and directly the representation to it. Yeah. I should double check, but it is surprising that it gets that. So I think so this is visual transformer. This is in fact kind of a BERT, only used between retraining, and this is a target. And oh yeah, I kept it. So this is the performance with the ratio of masking, and somewhere around 75% was the best performance, both during I think this was during the original training and during fine tuning. And as was mentioned, this is the original, I think, or maybe this is but this is at the first few layers, it doesn't get everything sharp, and then eventually it gets a lot sharper. And so this has been surprising for many people in the community that transformer will be able to do that. So that makes us revisit this whole GAN thing also. And also these representations start having a lot of information, because at test time, you will use not just the mask. I mean, unless you want to do regeneration, in this case, you use both the encoder and decoder. But in most cases, you just want a good encoder. And they showed that this encoder works on many data sets. But what's good for us in multimodal, and that's what we're going to talk about the last 5 minutes. Oh, yeah. What's your thought is? Yeah. So there's different hypotheses, and there's a few follow-up papers that looks at it. In the paper, they if you don't make it, if you have access to your exact neighbor, then you're always going to go with that shortcut. So if I don't hide enough, it becomes a very simple task. If I give you an image and only hide one patch, let's say, it's going to be an easy task, and you're going to be transformer. I mean, any deep learning or machine learning always go for the shortcut. So they're only going to take information very local. They're only going to really look at local information. It's only when you start being forced that really you need more than one. You need probably to really understand this. You need information from a lot of patches far. And so that's the intuition, at least. I think there's going to be more like understanding over the next few months about how exactly the first intuition, if you don't do enough, the transformer or any kind of will look very locally only. And so the embedding are going to be very local patches, and it's not going to understand holistically the image. So that's the intuition. But that's a good question, yeah. So there's a lot of discussions and follow-up work trying to understand exactly the domain adaptation or domain shift. Definitely, I'm sure in the training there were some animals that were someone with patches, maybe not that exact cause and exact location, but there has to be like, if really it has never seen that animal or any object that looks like that structure, it will be struggling. Now, what is interesting is that it seems that there's a little bit of generalization. You've seen two objects that kind of, your object is kind of a mixture of those two. I think they will be able to handle some of it, but here definitely it has to be from data. I mean, it cannot, the only thing it can do is take advantage of more than one object. And aggregate information from more than one object. But there will be a limit. If really you were to train only on BERT, like a BERT data set, and suddenly try it with cars, you're not going to get the same kind. You may get at least the contour or something like this, but you will not get the same yet. Okay. Then they go and multimodal, and that's the last 3 slides. Is now you can go multimodal. In fact, this is what the multimodal really, because now both image and text can be kind of a somewhat earlier fusion, because it's going to be patches of image and words. So this will be your by linear embedding in here. Why do they say linear embedding? Because a transformer at its base is a WQ, like a linear embedding. And so now you can both have image and text in the same. So this is BERT. And then this is my VIT, so visual transformer. And so I can put both of them together. I just need to differentiate the modality. Is it an image patch or is it a word patch? So in my embedding, I have an image or a word patch. Okay. And OT, this is last week. Optimal transport. Okay. So they use that optimal transport to see if they align each other. Optimal transport was to align 2 modalities together. So they use align transport. And finally, and that's really nice because that paper they show that the words, if you start looking at the attention between a word and which patch it was attending to, it starts having somewhat, not perfect, but somewhat of a mining. So cloudy, the cottage, the wall, it looks at different parts. So if you remember, a word and transformers, their whole job is contextualizing. So they need to decide which patch I'm relevant to. And so that's what you see here. And finally, the last one from NIREX, this 2021, which is really a nice paper. I think it's one of the reading assignment for next week. And ITM, don't even need to know. Everybody knows ITM. MLM, mask language model. So typical BERT. So it's BERT, BIT, and clip-ish. Yes, it's not exactly clip, but it's a clip-ish. So what they do is they do a clip, and then they do visual BERT, VLT BERT, not visual BERT, but VIT plus BERT here. So here they will align, and it's a decision is now you have for text, you remember you have the sentence embedding for text, and now you can do something like this for the patch. There is all your patches, and this is for the whole image. And then you do contrastive learning, like text and image, positive pairs are close to each other, negative pairs are far from each other. So this is related to kind of mutual information. And the last thing in that, and you will look in the reading assignment, is that they also did a hard negative. So this is a yes or no. Is the image match the text or not? That's the loss here. And then the small thing is they say, hey, if your mutual information is really close to each other, then sample more from there. That's probably a hard example to do. So you will sample, when you compute anyway your mutual information for the contrastive loss, you can use that information as a nice input to tell you, hey, don't select any negative, select the hard one, the most one. Okay, thank you very much for your attention, and see you on Thursday.